So we are dealing with the third problem in this series, and the problem is stating two small equally charged spheres, each of mass m, are suspended from the same point by silk threads of length L. The distance between the spheres x is less than L. Find the rate dq by dt with which the charge leaks off each sphere if their approach velocity varies as v equals alpha by root x, where alpha is a constant. So it is written as a or alpha, which is equal to constant. So we are beginning with problem 3.3. So we begin by drawing a necessary diagram for this situation, which is to be discussed. So over here we considered that this is a common support about which the two interacting masses, which is this one and the another being equal to this one, is hanged from a string of equal length. So we draw them as point masses. Now if these masses are identical, so this is the angle which we draw with the vertical, which we consider as theta over here, the charge being plus q and plus q. The distance between them is given to us as x. So using symmetry we can say that about this line the distance is x by 2 or x over here. So now if we identify the forces, the first force that is acting on this charge is electrostatic force on both the charges, which we mention as Fe. The next is due to gravity mg in this direction, and then there will be some tension in this thread, which we draw as T. Now the problem is also stating a very interesting point, which is asking us to consider that the distance between the spheres, which we are taking as x, to be less than L, that is the length, and then due to the charge is leaking from this surface, due to which the charges are constantly moving towards each other, and the velocity is given to us as v equals alpha root x or a root x. Let us take as a root x. So this is the problem which we say. So if we consider that the charged spheres are at equilibrium at every instant and the charge is decreasing, so the equilibrium distance x will also decrease. The equilibrium distance is also going to decrease, and if I draw FBD of one such sphere over here, so we can say that the two forces which we have discussed here are electrostatic Fe and then the weight mg, the angle being theta. So if I take this line, then I can say that this angle is 90 degree. So if this angle is theta and if we are considering a line perpendicular to this, so this angle will again come down to theta, and this is 90 minus theta. So if we break the force along this line, so net force along this line which we have drawn, let us say Mn, this must be 0. So if we break the component along this line, then we will have a gravity component mg sine theta in this direction and Fe cos theta in this direction. So for interaction of these particles, the way the problem is stating, where theta is assumed to be very small, that is x is less than L, so we can say that mg sine theta is equal to Fe cos theta. So at every point the charge is to be considered in equilibrium, and theta being very small, theta being very small, as per the data which states that x is less than L. So over here we can say if this theta is very small, then cos theta or the cosine of this theta value can be taken as 1, and sine theta can be approximated equal to theta or tan theta, and this can be written as x by 2L. So this distance will become x by 2 and L, so sine theta can be written as x by 2L, and if we put this value here, so therefore we can say mg x by 2L is equal to Fe, that is equal to q square upon 4 pi epsilon naught x square. So this is the necessary equation that we deduce by breaking the component along the line Mn and considering that the charge is decreasing, and so the equilibrium distance is also decreasing, and at every instant of time the particle is maintaining its equilibrium. Now the part of the problem is that it wants us to calculate the rate dq by dt with which the charge leaks off. So this is not the exact goal of the problem. The problem is asking us to calculate the rate at which the charge leaks if the velocity of approach is given to us. So for that part we again write the equation in terms of charge q. So if we break this equation in terms of charge q, then we can write it as q square L upon 2 pi epsilon naught mg is equal to x cube. Now since the rate of charge is given to us, so we can write it as q equals 2 pi epsilon naught mg by L square root, where all these parameters are constant, and x to the power 3 by 2. So if we differentiate this equation with respect to time, so differentiating with respect to time, so therefore we get dq by dt, that the rate at which the charge leaks off, is equal to, so this parameter is constant, 2 pi epsilon naught mg by L root over, and then we have derivative of x to the power 3 by 2 with respect to dt. So this can be written as dq by dt equals 2 pi epsilon naught mg by L square root 3 by 2 x to the power half, and then dx by dt. So where dx by dt will be written as velocity v, and therefore the final answer dq by dt can be written as 3a by 2, where dx by dt is written as alpha to the power alpha root by root x. So root x will cancel out eventually, and then we will have 3a by 2 pi epsilon naught mg by L. So this is the final part which the problem is asking us to calculate, the rate dq by dt with which the charge is leaking off. So this is the final answer that we have for this particular problem.